Welcome to this explainer brought to you by Forge College. Man, I am absolutely thrilled to get into today's topic with you all because we're about to build something literally every great engineer loves. We're building a wind tunnel. So if you've been following along, in our last lesson, we did the heavy lifting, right? We successfully translated our core logic from the EVM straight over to the SVM, mapped out the accounts, translated the errors, got that Rust code compiling, the whole shebang. But actually, scratch that. Now comes the absolute most critical phase. Before we even think about touching the actual blockchain, we need to construct an engineering wind tunnel for our newly ported smart contracts. We've got to see if they can withstand the intense aerodynamic pressures of the Solana network. You know, we've all heard that classic Web3 joke, right? Testing on mainnet is a feature, not a bug. Yeah, no way. Let's be absolutely clear here. Deploying the logic we just ported without putting it through a methodical, rigorous crash test, that is an incredibly dangerous game. Swapping out the underlying engine of your smart contract from Ethereum to Solana is, well, it's like a giant puzzle. It is complex. If we just throw it onto mainnet and cross our fingers, we aren't engineering anymore. We're gambling. So today we are going to learn exactly how to methodically crash test our code in a safe, completely local environment. Here is the blueprint for our laboratory today. First, the migration wind tunnel. Then, testing pure logic first, followed by mocking accounts and state. Next, faking CPIs and sysvars. And finally, the crash test debug report. All right, let's jump right into part one, the migration wind tunnel. Okay, so before we write a single assertion, we really need to understand why a simulated environment is absolutely crucial before going on-chain. Basically, we have to stop semantic drift in its tracks. See, when you move from EVM to Solana, your logic might compile perfectly, sure, but it might behave just a little bit differently. This early testing phase is going to catch those subtle differences. We're hunting for things like how reentrancy vectors change, how cross-contract calls behave asynchronously, or even how integer handling and math precision might differ between the two environments. For example, your Solidity contract might have relied on Ethereum's msg.sender in a way that just doesn't map perfectly one-to-one with Solana's signer privileges. Our wind tunnel exposes these semantic drifts long before they turn into million-dollar exploits. Moving right along to part two, testing pure logic first. Let's head over to the test bench. And honestly, my biggest piece of advice for you here is simple. Start small. We need to examine the absolute simplest, most isolated components in a complete vacuum before we wire anything up to the Solana runtime. And that brings us to the humble but mighty unit test. Now, a really critical detail here is doing this without a validator. We literally do not need the whole Solana blockchain running just to verify pure math. Think about it. If you have a function that takes an amount, multiplies it by a numerator, and divides by a denominator, well, we can completely test that in pure rest. The steps for this are highly deterministic and, frankly, beautifully simple. First up, you isolate the pure logic inside your crate. Second, write a pure Rust test using standard test macros. And third, just run cargo test. I mean, if your basic math fails here, it is going to fail spectacularly on-chain. And trust me, your users definitely won't think it's funny. We have to make absolutely sure these foundational gears work flawlessly before plugging them into the larger machine. It's fast, it's easy, and it gives you total confidence in your core algorithms. All right, next on the docket is part three, mocking accounts and state. So now that our basic gears are turning smoothly, it is time to build the surrounding machinery and simulate the actual state of the blockchain. If you're coming from Ethereum, you might be super used to a testing environment that just implicitly handles state for you. You know, you call a contract, the state effortlessly updates, easy. But on Solana, with the SVM, literally everything is an account. When we use tools like solana-program-test, we can't just assume state exists. We actually have to deliberately instantiate mocked accounts. We have to manually fund them with LAMP ports, assign owners, and precisely inject serialized state data. Yeah, it requires a bit more setup for sure, but the trade-off is that it gives you microscopic control over your environment. Here are our assembly instructions for getting that test context up and running. First, you build your program test harness. Second, register a mock key pair to act as your user or authority. Third, and guys, this is crucial, you inject the serialized state. I literally cannot stress this next part enough. Always, always use deterministic, seed-based addresses for your test key pairs and PDAs. Because if your tests are using random public keys every single time they run, oh man, debugging becomes an absolute nightmare. Determinism is the absolute key to reproducible tests. That brings us to Section 4, faking CPIs and sysvars. Okay, the harness is built. Now it is time to turn this wind tunnel to maximum speed and introduce some chaotic outside elements. In Solana, your program is very likely going to talk to other programs through cross-program invocations, or CPIs. But in our local test bench, those other programs might not even exist. So what do? We use a CPI mock. Basically, this means registering a fake program ID in our test environment that returns carefully controlled results. We can tell it to succeed, or we can intentionally force it to fail, just to see how our ported contract handles the error. Similarly, we can use program test helpers to manipulate system variables, or sysvars, like the clock. You want to see what happens when your contract thinks it's the year 2099? Well, you can mock the clock sysvar and force that edge case right here, right now. When we're going through our integration checklist, specifically for something like an account balance update, we assert that the token balance delta matches our expected transfer. Pretty standard. But looking further down the table at state serialization, please do not just check if the raw Lamport balance changed. You have got to verify the exact deserialized struct fields. Does the Boolean flag correctly flip to true? Is the mapped address perfectly aligned? And finally, for CPI response handling, assert that your program hits the correct error branch when the mocked CPI actually fails. This is what proves your error translation from the EVM holds up under real pressure. Let's move to Section 5, the crash test debug report. So what exactly happens when the prototype clunks, grinds, and completely fails on the test bench? Look, we need to normalize failure here. When a test fails, we do not panic. We calmly approach the wreckage and extract the black box data. To get that data, you need a robust debug report. Here are the precise ingredients you need. Document the exact test command used. Record the exact seed and key pair values, so the failure is perfectly reproducible. Note the specific failing assertion. Then, and this is absolutely vital, grab the program transaction logs. In solana-program-test, you can easily extract these using banksclient.etTransaction. Finally, write down your suspected cause. A test failure without this data is really just a complaint. But with this data, it's actionable engineering intelligence. Now, if you're wondering what usually causes these crashes in the first place, let me give you a rapid-fire rundown of the most common culprits I see when porting from EVM to SVM. Number 1, mis-serialized layouts. This is super often due to ABI encoding differences where the byte order or padding doesn't match what your Rust code expects. Number 2, wrong authority key pairs signing the transaction. Number 3, trying to read or write to uninitialized account data. And number 4, unchecked math causing a panic. For sure, check these 4 things first when your harness crashes. Finally, Section 6, Flight Readiness Review. We are wrapping up the testing laboratory phase and preparing for the final evaluation of your capstone deliverable. So here is the ultimate question for us. Is your program ready for mainnet? Look, if your local unit and integration tests are passing smoothly, you are in an amazing spot. But I really want to reassure you, if you hit a wall, a perfectly documented, deterministic, reproducible failure, complete with a solid debug report and a clear plan for how to fix it, that is still a highly successful capstone outcome. Engineering is all about understanding the boundaries of your system. A reproducible failure is really just a success waiting to happen. Now that we know the logic works and is safe, it is time to make it fast and cheap. But ask yourself, is your perfectly safe contract going to bankrupt your users in compute fees? Next time, we'll dive into performance considerations and optimization. I want to thank you so much for joining me in this explainer created by Forge College. To learn more about this subject, dive deeper into Solana development, and explore a wealth of other amazing Web3 related topics, please visit our website at forge.college. Keep testing, keep building, and I'll catch you in the next one.